Hello. In this example, I'm going to show you how we can write a recursive function in order to get the nth number of a Fibonacci series. We all know what Fibonacci series is. Here it is. Here the first two terms are fixed. The first one is 1, the second one is 1 again, and from third onwards it's the sum of the immediate previous two numbers. So that's why the third is 2, and then 2 plus 1 is 3, then 3 plus 2 is 5, and it's going on. So we need to write a function that's going to return the nth Fibonacci series. So if I supply 1 to that function, it's going to return me the first number of the Fibonacci series, and that's 1. If I supply 2 as parameter to the function, it's going to return 1 again. And if I supply 3 as the parameter, it's going to return me 2, because that's the third term. So if I supply 6, then the sixth term of the Fibonacci series is 8. It's going to return me 8. So let me just write the function. So it should be returning a number. So it can be, the return type should be long, because if the term number is high, then it's going to be a big number. So get term, get fib term, that should be the appropriate name of the function. Now if the value for t is 1 or it is equals to 2, then the case is trivial. That means in both the cases, if it is term number 1 or 2, in both the cases it is actually 1, so we are returning back 1 to the caller. Otherwise, if it is not the first or the second term, then we should go on and find out the previous two terms and add them and return the result back to the caller. So we should find the immediate previous two terms. For that, again, we just call the get fib term function and supply t minus 1. Now this is going to return me the immediate previous term, and I'm calling get fib term with t minus 2. Then it's the previous to previous term that will be returned back. So we are just adding these two values and we are returning this to the caller. So that's the recursive call. We are doing the recursive call twice here. You can see that this is in order to find out the immediate previous term, and this is to find out the previous to previous term. So they are going to return the immediate previous term and the previous to that, and we are adding them and returning the result to the caller. So that's it. So now if I go on and call this function, so I will get the nth term of the Fibonacci series. I'm just using a for loop in order to print the first 10 terms. So the value for t is 1, then it's the first term, t is 2, it's the second term, and so on. So I'm just executing this, and here you go. We get the first 10 terms of the Fibonacci series. Hello, welcome back. We are learning recursion. Now in this tutorial, I'm going to develop a recursive function in order to implement Tower of Hanoi game. The function is supposed to print the necessary steps. If followed, then the Tower of Hanoi problem could be solved for n number of disks. Possibly we all know the game. We have played this in our childhood, and if not, then you can just go and Google about this Tower of Hanoi game. The history is also interesting. And the myth associated is also interesting, very much interesting. And you can go and Google and get all the information regarding this Tower of Hanoi game. So here is the game. We have these 3 pegs, position 0, position 1, and position 2. And in one peg, there are n number of disks. Here it is 3 in position 0. We need to transfer all these disks to a destination tower. Destination could be position 1 or position 2. That doesn't matter, the problem remains same. So if the destination is position 2, then we can use the position 1 as auxiliary tower, and we need to transfer all these 3 disks to position 2 using that auxiliary tower position 1. But there are 2 conditions. Number 1, we cannot pick more than 1 disk at a time from any peg. And number 2, in the process of transfer, we cannot put a larger disk on a smaller disk. That's prohibited. So how could we do that? Actually, if there are 3 disks, then it's easier to guess where the first disk, that means the disk at the top, the green one, is going to be placed, at the very first move, we can just go and back calculate to get position for the first disk, and we can just go and play to solve. But if the number of disks is higher, that means say n equals to 15 or 10 or 12 or even more, then it's really tough to guess where the first disk is going to be placed in the first move and where the second one is going to be in the second move. So they are really going to be tough. So in such situation, what we do, we actually go in the reverse order. We think it in a structured way, and the solution could be achieved by thinking in the reverse order. Here, if we need to transfer all these 3 disks, you can see that this from position 0 to position 2, then this after transfer, this blue disk will be placed at the bottom of this position 2. That means this will be transferred here at the bottom. Then on that the red will come, then on that the green will come. So one thing is clear, that the blue disk has to be at the bottom. If we just need to transfer properly for any n, then the bottom disk has to be placed at the bottom, and the disk just on the top of the bottom will be placed exactly on the top of the bottom in the destination. So for that, what we need to do, we need to transfer all these n-1 disk from this source tower to the auxiliary tower. If we can do that, then this disk becomes free, because we cannot pick this blue disk at the very beginning because there are these 2 disks on it. So we need to transfer this n-1 disk to this auxiliary tower, that means position 1. The red and the green will appear here. So this is red and this is green. I'm just writing this. And in that case, this blue is going to become free, and we can pick that and place that to the destination. That means in that case, when these 2 are removed, then we can pick this blue and can place it here, because that's 1 disk left. Now we have this green and red left here. Now we need to get back this green and red here in this position 2. Now that we cannot do in a single go. Again, the problem has been reduced, as you can see that. Now the problem is that this is the source tower, this is the destination tower, and this will be the auxiliary tower because that is empty at that point. So we need to remove this disk, that's n-1 equals to 1, to this auxiliary, and we will become free. The red will become free, and we can just move that to the destination, that means position 2. And in the next move we can just bring back the green on the top. So actually the problem is reduced at each point. So in order to just pick this blue disk, we need to remove these 2. In that case, the problem is reduced to n equals to 2, and in that case the source tower is this one, the destination is this one, the auxiliary is this one. So we need to move these 2 disks from here to here, so the Tower of Hanoi problem gets reduced. So in each time we will be having a reduced problem with lesser number of disks and varying pegs. The recursion can be used, and the trivial case is that when there is only 1 disk left, we can just pick it and place it to the destination. So let's see how we can do it programmatically by writing the recursive function. But before that, I would like to play this game and to show you it's really amazing. So for the first time, I'm just placing it on the 3rd, and then the red comes here, then the green comes here. So you see that we have removed all the 2 disks on position 1, that was the auxiliary. Now we can just move this to the destination. That's free. We can just pick it and place it to the destination. Now we are left with these 2 disks in position 1. So we need to get them to the destination. So for that, now the problem is there are 2 disks and the source is this one, destination is this one, and this is the auxiliary. So just pick this disk, put it to the auxiliary, move this to the destination, and then move this to destination. So we are done. Now I'm going to write the function in the next tutorial. Thank you. So here we go with the implementation of Tower of Hanoi. Now if we go on and call the Tower of Hanoi function that I'm supposed to write, so we'll be passing 4 parameters. First one is the number of disks. The second is the source tower at the very beginning. Say it's the tower number 1. Then at the middle I'm passing tower number 2, that's the auxiliary tower, and then I'm passing the destination. So the structure of the parameters are clear. Now if we just pass 1 here, that means the tower of Hanoi function should print all the steps required to transfer one disk from tower number 1 to tower number 3 using tower number 2. So if I just write 5 here, that means tower of Hanoi function is going to print all the necessary steps to transfer 5 disks from tower number 1 to tower number 3 using tower number 2. So if I just go on and change it something like this here, then the meaning is straightforward. There are 5 disks at tower number 2. We need to transfer them to tower number 1 using the auxiliary tower 3. So if there are 3 disks and we go on and pass say 1 here, 2 here and 3 at the middle here, then it means there are 3 disks at the beginning in tower number 1 and we need to transfer all these 3 disks from 1 to 2 using the tower 3. So here is the implementation. First of all, it should not return anything. It's going to print the steps into the console. So the name of the function is TOH and it's going to receive the number of disk. N is the number of disk, then the source tower, then the auxiliary tower, and the last one is the destination tower. Okay, now if the value of n equals 1, that means 1 is passed as the number of disk, then the case is trivial one. We need to pick the disk and place to the destination. We need to pick the disk from the source and need to place it to the destination because no other disk is available on it. So it's trivial. Just pick and place. So I'm just writing a printf statement. Move the disk from %d tower to tower number %d to tower number %d. So here it's going to be source to dest. Okay, and we should return back to the caller. Whoever calls this is the last case. We have placed the last from the source to destination and we are returning back to the caller. If not, if there are greater than 1 disk, that means if this fails, then we come here. In that case, we need to move all n-1 disk to auxiliary, and for that we can call the same tower of Hanoi function. n-1 is the number of disks that should be moved from source to auxiliary. Now you notice this, we are passing aux at the place of destination because this is the call that's going to transfer all n-1 disks from source to auxiliary. So destination can be used as auxiliary in this case, so we are passing destination at the middle. So this particular call is going to remove all the n-1 disk in recursive fashion again from source to auxiliary tower. After completing this call, then there is only 1 disk left because we have transferred all n-1 disks to the auxiliary. So we have left with only 1 disk, and in that case we can just use the tower of Hanoi and we can pass 1, and the source is source, the aux is aux, the dest is dest. So this is going to transfer the single disk from source to destination. That means in that call this is going to be true and this particular printf will do the printing. Now on transferring that single disk to the destination, we need to complete the task by moving all the n-1 disks that was kept in the auxiliary tower to the destination. So for that, just call the tower of Hanoi, move n-1 disks from auxiliary tower to the destination tower. So in this case we can just use this source as auxiliary tower. So this last call to the tower of Hanoi, again in recursive fashion, will move all the n-1 disks that were kept in the auxiliary tower to the destination tower. So now if I go on and execute this program, it's going to print all the steps for transferring 3 disks from tower number 1 to tower number 2 using tower number 3. Or if I just change it, so in this case it's going to print all the steps to move 3 disks from tower number 1 to tower number 3 using tower number 2. Let's see this. You can see that if you go on and follow all these steps, then you will be able to transfer 3 disks from 1 to tower number 3. Now if I just change here, I am just placing 2 and placing 3 here, be the steps to move from 1 to 2 using 3. So you can just check this manually. Now one more thing that I would like to mention at this point is that if there are n disks, then we can just mathematically calculate and say that there are obviously 2 to the power n minus 1 number of moves. That means if there are 3 disks, then there are 7 moves. If there are 4 disks, there are 2 to the power 4, means 16 minus 1, 15 moves. So it's actually the order of 2 to the power n, the number of comparisons. So it's huge if we are having huge number of disks. So it's going to take huge amount of time. Even with the fastest computer of this era, if we are supplying say 64 disks, that's number of disks which is coming from the myth, then it's going to take say about 500 years to complete the whole task. Now let me just complete this commenting. So that's it. We are done with the implementation of Tower of Hanoi, and in the next tutorial I'll be giving you some more example on recursion. Thank you. Hello everybody, this is Shivaji and we are critically evaluating recursive function call versus iterative approach. So far we have learned what tail recursion is, and we have found that tail recursion is just equivalent of writing a loop. No extra overhead or burden is there with the tail recursion. And we have also seen that in case of non-tail recursions, it's better to write loop. If you need to implement a particular logic using a non-tail recursion and you have an equivalent loop to solve the same thing, then it's better to go with the loop, because the non-tail recursion is going to bring in the overhead of stacking activity in the memory. Now we need to understand when exactly we need to go with the recursion instead of iteration. So there are situations when we explicitly need a stack in order to solve a problem. So in such cases, we would require to implement the stack by ourselves, and that will just increase the number of lines of our code in our program. But since we know that there is a stack in the memory that the system creates in order to maintain the recursive call, so we can use that stack instead in order to preserve our values and can do away with the writing of our own explicit stack. So that will just reduce the number of lines of code, and we will be beneficial in such cases by using recursion. Let's have this example. Say we need to write a program in order to print the binary equivalent of a decimal number. The traditional way for doing this is just to divide the decimal number by 2 and collect the remainder and print it in the reverse order. So say we need to find out the binary equivalent of decimal number, say 12. Then we will go on dividing it with 2 and we find that the remainder is 0. We need to store this because this is the least significant value. And then again we will go and divide 6 by 2 and we get 3. So again we are having 0 as remainder, and again we are dividing 3 by 2. So here is 1 and we have 1 as remainder. Again we divide it by 2, we get 0 and 1 as remainder. So now if we print in the reverse order, then we get the binary equivalent of 12 as 1100. This is the binary equivalent of 12. But in order to perform this programmatically, what we need to do, we need to have a stack in order to store the remainders. So we will be using the stack, otherwise it's not possible. As you can see that on each division, after each division, we need to store the remainder and we need to get it in the reverse order. So what we will do, we are getting the 0 here, so we will have a stack and we'll push 0 into the stack. Then we are again having 0 as remainder, we'll push 0 again, and we are having 1 as remainder here, so we will be pushing 1 here, and again we have 1 at the last time, so we'll be pushing 1 again. So now from this stack we'll be popping the elements and we'll be printing the elements into the console. So stack is very much required to find the equivalent binary number for a decimal. Without this stack we cannot do this. So in order to implement this stack we need to write code, and we need to write the push operation, pop operation, and all the maintenance has to be done for this stack. But if we are going with recursive solution in order to find out the binary equivalent of decimal number, then we can do a way of writing this stack explicitly, and we can use the system generated stack for maintenance of recursion, for keeping these values, for keeping our desired values that we need to preserve for our program. Let's see how we can do that. Now before going to that, you need to understand one more thing, that we can find out the binary equivalent of decimal number just because of the fact that it's recursive in nature. If you can see that, say I'm having this 10, I want to find out the binary equivalent of this 10, and binary equivalent of 10 is actually binary equivalent of 5, and then the result of having this 10% 2. Binary equivalent of 5 is 101 and 10% 2 is 0. So you can see that this is the equivalent of 10 in binary. Now how do you find out the binary equivalent of 5? It's again recursive. So binary equivalent of 5 is actually binary equivalent of 5 divided by 2, that is 2. And then we need to just print or have this 5% 2. So binary equivalent of 2 is 10, and this 5% 2 is 1. So binary equivalent of 5 is 101. That's the binary equivalent of 5. Now how you to find the binary equivalent of 2? That's binary equivalent of 1. That's 2 divided by 2, and then 2% 2. So it's recursive. So we can just use the recursive function call in order to find out or print the binary equivalent of a given number. First of all, what we need to do is to check whether this value is 1 or not. If n equals to 1, we can just have this case as the trivial case, because the binary equivalent of 1 is always 1. So you can just go on and print 1 and can terminate the recursion, and you can just return back to the caller and terminate the recursion. Otherwise, if it is not, then we need to find out the binary equivalent of n by 2. That should be done first. So dec to bin, it should first find out the binary equivalent of n by 2. If that is printed, then we can just go on and print n% 2. So here we are done. That means in this case you can see that it's, if I say I pass on, let me just type this, say I pass on dec to bin, and I'm passing on say 10, it will print 1010. That's the binary equivalent of 10. Let me show you that, then I'll explain. Oh, that's because of the fact that I have used this \n. I'm running again. Here you go. You can see that it's 1010. That's the binary equivalent of 10. So if you write 12, it's going to be 10. It's 1100. That's the equivalent of 12. So how we are solving this? Actually, say it's 10. Then what we are doing here? First call here it is 10. So we are just going and finding out the binary equivalent of 10 by 2. That's 5. And that is printing 101. And then on coming back from that recursion, we are finding 10% 2, that is 0, and we are printing 0. Now in this next call, when it is receiving 5, it's actually 5 by 2. We are actually printing, in order to print the binary equivalent of 5, what we are doing, we are calling dec to bin in order to print the binary equivalent of 2. 5 by 2 means that's 2 integer division. So this particular call 5 by 2, when you passed to this dec to bin, it's printing 10 because that's equivalent of 2. And then on coming back, what we are doing, we are finding out 5% 2, and that is 1. So in this way, when it ultimately reaching n equals to 1, it's actually printing 1 and returning back to the caller. So you can see that we just did a simple recursion and we we are printing the binary equivalent of decimal number, and we are not implementing a stack by ourselves. Had we not used this recursion, we would require to write the push and pop operation for a stack and the stack itself in order to convert the decimal value to the equivalent binary. So here the number of lines of code is really very less. Otherwise, if we would adopt the iteration technique, it would be really large, because stack creation, maintenance, push, pop operations would have to be written by ourselves. So when you need the explicit stack, it's better to go with the recursion. And in each recursive call, we will be using the stack, the system generated stack, in order to push the value into the stack. Here you can see that we are using the system generated stack, because when this particular function is called recursively, the current n is pushed into the system generated stack, and when we are getting back, we are popping the system is popping the stack and getting the actual value of n for this instance and using that. So you don't need to write the stack at all when we are using recursion. So it's beneficial to write recursion when we need explicit stacks. With this, we come to the end of this discussion, and in the next tutorial, I will be showing you some more example on recursions. Thank you. Hello, this is Shivaji, and we are critically evaluating recursive function call in this section of our C learning procedure. Okay, this was the previous example that I have talked in the last tutorial. This was printing from n to 1, and we have discussed how this is happening in the memory and why this is called tail recursion, because we have this recursive function call as the last statement of the function. So now if I just need to modify this, instead of printing from n to 1, if the requirement is to print from 1 to n, then you just cannot print the value of n right here, because you are receiving n and immediately we are printing n. In that case, it's going to print from n to 1. We are decrementing n and going to print the decremented value in the next print number. But if we need to print from 1 to n, and first of all we need to recursively go up to 1, and then we need to start printing and go to the previous one to print 2 and go to the previous one and get back here ultimately at n. So we just cannot print before the recursive call. We need to print after the recursive call, because we need to go to 1 first, then on the return path we need to print the value of n. So this is not going to do that work for us if we need to print from 1 to n. In that case we need to modify, and after the recursive call we need to print the value for n. Another modification that we need to do here, we cannot decrement n by 1, as that's going to reduce n locally, and for that what will happen, we will ultimately print n minus 1 instead of n here. When we get back from the recursion, it's going to be finally n minus 1. But we need to pass on n minus 1 to the next print number recursive call. So it should be n minus 1. So we are not changing n, but we are passing on n minus 1 to the next call. So now in this case, it's going to be 1 up to n. Okay, in this case, it's 1 up to 3. So let me show you that. You can see that it's 1, 2, 3. So what is happening here, we are just going to the recursive call first prior printing the number. So we are passing on n minus 1, and eventually n minus 1 becomes 0. When the value of n becomes 0, then the control returns back to the previous instance, and in the return path it is printing the value into the console. So let me show you the stacking activity in the memory for this recursion so that you understand better. Okay, so when the first call takes place, obviously the main is pushed into the stack, and the first call takes place here. Value of n is 3 here at per this example, and n is not equals to 0, so the return is not executed, so it comes here, and you can see that there is a recursive call, print number, and we are passing on 2. Now since we are using n after getting back or completing this recursion, when we get back here, this statement is going to be executed next after completing this print number function call. So the value of n has to be preserved. This is not a tail recursion. This recursive call is not the last statement. Had it been the last statement, the operating system would not require to store the value of n at all. But in this case, since we are using n after this recursive call, so n has to be preserved. And what operating system does, it pushes the status of the current function that includes the variable n as well into the stack. So n equals to 3 is pushed into the stack, then the function call takes place. So you have this function call. The next one, for n equals to 2, we have this print number instance here. Here the value of n received is 2, and again the if is going to be false, it's not going to be executed, the return is not going to be executed. Okay, and we have this print number again, the recursive call, and here again we are passing n minus 1. N is 2 here locally. So on getting back from the recursion, we are printing the same thing here as well, because the same code is replicated. So here this recursion will take place, but prior to go to the call, operating system is going to store this n into the stack as well, because on getting back it's going to use the n. So n equals to 2 is again stored into the stack, and it goes to the next print number. And here the n received is 1. Again we have the print number statement here, and we are passing on n minus 1. N here is 1, so n minus 1 means 0. That's going to be passed to the next print number call, and we have that printf statement as well. So here, when it is going for this call, prior to that n will be stored into the stack, and that's 1. So now the print number n for the last time is called, and here n is 0. Now since here n is 0, so this if condition is going to become true, and the return is going to take place. So now operating system, in order to return the control, will look into the stack. It gets everything of the previous function at the top of the stack. So it deletes this top, retrieves every information, that where it should return, what's the value there. So it gets back n equals to 1 and gets back here after this print number statement here, because this was the last instance of print number that was called prior to this n equals to 0. So on completing this, and when it gets back here, the cycle is complete. So print number, printf, this statement is the next one, so n is printed here. So the 1 is going to be printed first time from this printf, because n is 1 here. Now the call is complete. Now this instance is complete, so it again looks into the stack and it finds n equals to 2 there, and it gets every information of the previous instance that was kept here while going for the call. So it deletes this and it comes back here. This is the next statement for n equals to 2. This was the instance. So here it prints n equals to 2 and it completes this call. Then it again looks into the stack and finds the previous instance and again deletes that and gets back here. That was the previous to this. And this printf is called now, and here the value of n was 3 that was retrieved from the stack. Okay, so 3 is printed here and it gets terminated. So when it gets terminated, it looks into main, looks into the stack, it gets main, everything retrieved, and again it continues with the main. Whatever the instruction that you have here will be continued. So this is how the stacking takes place when this particular recursive call goes on, or something like this will go on. So now you can see that there is an overhead in order to carry on this recursive call. So which one is better for this case? If we would write a for loop, then this type of stacking activity will not be there. We can still print from 1 to n by using a simple loop. So which one is better? Obviously the loop is going to be better as far as this particular example is concerned. We can just write a simple loop in order to print from 1 to n, and that's not going to have any kind of push and popping activity and this kind of maintenance of stack in the memory. So it's better to write a for loop in this case instead of having the recursion call as far as this particular example goes. Therefore, if we can write a for loop to solve a problem, and we are also able to write a non-tail recursion to solve the same problem, then it's always better to go with the loop. Because if you go with the recursion, then it will bring in the overhead of stack management in the memory. But there are cases when you cannot solve a problem using a simple loop. You'd require to implement stack explicitly. There are some cases. In those cases, it would be always beneficial to write a recursion, because we will be using the system generated stack, the stack that will be created for performing the recursion. We will be using that stack in order to store our own values, and in that case the recursion is going to reduce the number of lines of codes to large extent, and we won't require to implement the stack explicitly. So recursion is going to help us in such situations when we need a stack explicitly in our program. So in that case, the recursion is going to be beneficial. We'll see that in the next tutorial. Thank you. Hi. Now we need to understand why recursion. We actually can do the same thing using a simple for loop, but why should you go for recursion? Is it beneficial to adopt a recursive approach in our program, or it is better to stick with the iterative technique using a for loop or while loop? So that's a critical discussion, and I'm going to give you some examples in this video and in the next couple of videos so that you can understand clearly when to adopt recursion and when to adopt iteration. So I've just modified the example of the previous tutorial a bit. Here I have just omitted the hello world printing message, and the rest of the things are just same. So it's going to print 3, 2, 1 in this case. That means I'm passing 3 here. So let me just change the name of the function as well so that it's become meaningful. I'm just changing it to say print number. Okay, and here it is print number, and the recursive call is also to print number. Okay, so now what it is going to do, it's going to print from n to 1. That means if I pass on 3 from main, then 3 will be received here, 3 will be printed, then oh, I need to decrement the value of n as well. That is a mistake. Okay, just let me decrement the value of n by 1, n minus minus, calling the print number function and passing n here to the print number. So in the next call it's going to be 2, and then it's 1, and eventually when n becomes 0, the return statement will be executed and the recursion terminates. Okay, now let me just show you what happens in the memory when this call goes on practically in runtime. So first of all, when this first call is going to happen, operating system obviously is going to create a stack, and main will be pushed in the stack. All the details of the main function will be pushed into the stack, and the first print number is called. So here the value of n is 3. Now n is not equals to 0. Okay, so that return statement doesn't take place. So here it comes and prints the value of n, and that is 3. That will be printed. Value of n is decremented by 1, 2, and again we are calling the same print number function with 2. So the next print number function is called from here, and I'm just writing n here without that unsigned integer just to make it simple. Okay, here the value of n is 2. This is the same function, but the instance is different. That means this is there in the memory, this is again created another instance, and this is also there in the memory. So when the call goes here, in the traditional function calling case, operating system would require to push the status of the current function into the stack. But here, as you can see, that it's the last statement from where we are just calling the function itself. That means the recursive call is made as the last statement of the function. On completion of the recursive call, when the control gets back here, we do not have anything left to do in the function. So in this case, operating system is not going to store anything into the stack because that's not required. Actually, on getting back, we don't have anything to do. So the operating system is not going to push anything, and compiler never generates the push instruction in such cases. Compiler is a clever one actually. It inspects the code and generates optimized code. So in this case, push operation for this function call doesn't take place, and again here the same code is executed. The same code is there. N is 2, so it's not equal to 0. The return is not executed. It will not be executed, and then printf will print 2. Here the printf goes ... Okay, so it prints 2, and then the value of n is decremented by 1 and it becomes 1, and then again we are calling the same print number and we are passing n here. So the value of n that is passed here is 1. So again another print number will be called. That's the next one with n equals to 1, and here also the same code is there, and the value of n that is printed, going to be printed from here, is 1, and then the value of n is going to be decremented to 0, and now the final call to the print number is going to take place where we are passing 0 here. So in this case, when this particular print number is called, then n is received as 0. So now this is going to be executed. So the return statement is going to take place right now, executed right now, because n is 0, this is true, and the return statement takes place. Now the point is that where it's going to return. Is it going to return to the immediate previous print number? So the operating system is going to look into the stack for where it should return. So, and it finds main there because we do not have anything left in the callback path to do in these functions, because print number was the last call. So it looks into the stack and it gets main. So the main is deleted from the stack and the control gets back here. So in this kind of recursion, where the recursive call is made as the last statement, this is typically called tail recursion, and no stacking activity is there for the recursive call. So there is no overhead for the operating system. Had there anything left after this recursive call, then operating system would require to keep the status into the stack by pushing the current function information each time on recursive call, and that would create the overhead. That would definitely affect the performance. But here there is no stacking activity, as the recursive call is the last statement, so it's just equivalent with the for loop because it's doesn't have any overhead. So if you can write a tail recursion to do something instead of a for loop, then the for loop or any loop is just equivalent with the tail recursion. That means a tail recursion and a loop, they're just equivalent. So it's your choice. You can write a tail recursion or a loop. That's okay, no problem. You can go in either way. But there are situations when you won't be able to write tail recursion at all. The logic of the program or the need of your code may force you to write non-tail recursion, and that means you won't be able to implement the logic using tail recursion. In such cases, you need to think properly what to do, recursion or loop. I'll be discussing that in next video tutorial. So here you go, I'm just running this and showing you that it's printing 3, 2, 1, and you can see that it's 3, 2, 1. Done. Thank you. Hello, I am Shivaji and you are in a process of learning C programming with me. In this tutorial, I am going to introduce recursive function call to you. In recursion, a function calls itself, and that we call recursive function calling. As an example, you can see that we have a function print message here, and from within the print message we are calling the same function print message. So this is a recursive call. Here we are making the recursive call. So what will happen here, on calling the print message function, the hello world will be printed for the first time, then it will go on calling itself. So, and this in this case is going to be for indefinite number of times unless and until the system denies to call due to some resource failure. So it will go on printing hello world for indefinite number of times. So this is a recursive function call, and that we can use in our program to go or execute same set of code again and again and for a desired number of times. So if we need to implement recursion fruitfully or effectively, what we need is to curve the recursion call so that recursive function call is going to be only for desired number of times. So for that we need to just curve the recursive call by putting some condition which is not available in this case, so it's going to be indefinite. So for effective recursion, the termination condition of the recursion is very much important. So say, for example, we want to put it in this way. Say, if I call the print message function and I will pass a number here. So if I pass 3, from the calling point, then print message is going to print hello world for 3 times. So we need to check how many times the print message has been printed. Now if it is calling itself for 3 times, then it's done, and then we need to terminate it. So let's see how we can do that. We are receiving n here, the parameter that is passed to the function. Now the trivial case is that if the value for n is 0, then it should not print anything, because we are passing an integer to the print message, that is the number of times the message is to be printed into the console. So if the number is 0, that means it should not do anything and it should just return back to the caller. That's the trivial case, a straightforward case. We are not supposed to do anything if the value of n is 0. If the value of n is not 0, that means it's greater than n. In order to ensure that the value of n is positive, so what we are doing, we are just receiving unsigned integer. So here the hello world will be printed for the first time. Say if the value of n is 3, then what we are doing, we are just printing the hello world for the first time, and then we are decrementing the value of n by 1, and we are passing it on to the next recursive call. So you can see that for the very first time is 3 here in our, as per our example, because we have passed 3. So it's not equals to 0, so it's not going to be returned back to the caller. Hello world will be printed for the first time. I'm just writing it, and then the value of n is going to be decremented to 2. So in the next print message, that means here 2 is passed to the print message function, so the next print message that we are calling here will receive 2, and in that case here it is 2 is the second instance of the same print message, so it is receiving 2 here. So again it's not equals to 0, so hello world will be printed from the second instance, so here it will be printed, and then the value of n is going to become 1. So again you are calling the same print message function and passing 1 here. So for the third call is going to be 1 here at n, and again n is not equals to 0, so the third time print hello world, this printf is going to print the hello world, and then the value of n is going to become 0, and again we are calling the print message function. Now this time the value of n is 0, so this condition is going to become true, so the control is going to return back. The recursion is going to terminate at this point of time. So this condition is called recursion base condition, from where if it is true, then at that point the recursion bounces back to the caller. So it will ultimately eventually come to this main, so it will go back to the control will get back to the main function after completing this. So 3 times the hello world is going to be printed into the console. So this is how the recursion works. We need to put a termination condition so that the recursion eventually terminates according to the need of our execution or code or our logic. So this is the recursive call, and now I'm going to execute this program to show you that it's really printing hello world 3 times into the console. Here is the output. You can see that hello world has been printed 3 times. So if I just pass on 5 here, it will be 5 times the hello world printed into the console. Here it is, you can see that. In order to make the thing more comprehensive, what I am doing here, I can just print the value of n along with the message. So in that case, for the first time the n is going to be printed 5, and in the next call it's going to be decremented to 4, so the value of n will be printed as 4. So it will go on up to 1, you can see that, and then eventually the value of n becomes 0. So in the last call this recursion base is true, base will be true, and the recursion will terminate. So here it is. I'm sorry, should be %d instead of %n. Here you can see that it's 5, 4, 3, 2, 1. So the value of n is printed. So in the next tutorial I will be giving you some more examples with recursion, and then we will dig deeper to understand what happens in the memory when a recursive function call practically goes on, and what is tail recursion, and also we will understand I will understand clearly when to adopt recursion and when to adopt iteration in our program. Hello everybody, welcome back. Before I go and tell you everything about recursion, prior to that, we need to know what happens in the memory when a function is called. Operating system behind the screen does a lots of things in order to implement the function call practically. So we need to understand that what happens in the memory, what goes there in the memory when a function call takes place practically in runtime. So here you can see that we have an example here. We have the main function where I have declared these variables I, and there is an array x that is initialized with 3 values and a function and a variable sum. So from this particular point I am calling the fun1 function for some purpose. Now when the control is going to be transferred to the fun1 function, that means the function call is going to take place practically in the memory, then what the operating system is going to do, it is going to push all the information of the current function, that is the main function, into the stack. So operating system is going to create a stack in order to keep the details of the current function, because when we are going to the function fun1 from main is not completely done. After completing the call of fun1, the control is going to get back to the main. That means this particular line will be executed after completion of the fun1 function. So operating system needs to remember each and everything in the main. It needs to remember that there is an array x and the data item that is contained in array. There is a variable sum and I, what are the values there. So everything has to be preserved. The state of the current function has to be preserved. So operating system creates a stack and pushes all the information regarding the current function into the stack. So this is a stack. We know that stack is a data structure, that is last in first out data structure. Now a simple example of stack is a stack of books. If you go on stacking books one after another, then whenever you try to pick a book, you are always going to get the lastly placed book on the top of the stack. That's the property of the stack. The elements in the stack follows last in first out order. So stack is a typical data structure that can be implemented. So operating system builds this stack according to the instructions written by the compiler, and it pushes the status, it pushes the state of the current function into the stack. Here it is the main function's information will be pushed into the stack, and then the function called fun1 takes place. So then it goes to function fun1. So now when the operating system is executing this fun1 function, now there may be a call to another function fun2 from within fun1. It may happen. We may need to call some other function in order to do some other task from within fun1. So in that case, all the information of fun1 will be pushed into the stack. What are the variables there? What is the return value? And what is the next instruction that is to be executed in fun1 after completing fun2? So every information will be pushed into the stack by the operating system. So let me just write the fun2 for your convenience so that you can understand better. So we may have another function call here in our program. Say I'm calling the function fun1, and say we have a variable p equals to 10 here, and we are calling the function fun2, and again we are getting the return value from fun2, and we are doing something with the variable p after, say, we are incrementing. These are all fictitious. That means this type of codes can be there in your function. So I'm just writing that in order to make you understand that what happens clearly. Now I'm writing the fun2 function. So here we may need to do something. Say, okay, then ultimately a value is returned back. Say we have a variable k here, and we are doing some processing, and we are returning ultimately the value of k. Okay, that makes sense. So we are going to the function fun2 here. So all the information of fun1 is going to be kept into the stack. Then the control jumps to the function fun2, and on completion of the function fun2, what happens? The operating system pops the stack. So the top of the stack is fun1. So operating system gets to know that it was the fun1 function that was lastly called. So it removes every information from the stack. It gets back all the information regarding fun1 and continues from here after that, means, and assigns the value back to p and then continues here. So on completion of fun1, again the operating system pops the stack and it gets the details of main. So it gets back here and it continues after this. So during the function call, whenever the function call takes place, each and every information of the current function that is necessary to keep will be preserved in the stack. So this is the phenomenon that is actually performed by the operating system behind the screen to make the function call successful. Now, there are some situations when the stacking is not required. Practically, it's not required. So for example, there are situations, I'm giving you another example. Say we have something like this. Say we have a function named fun3 and we made the call to the function fun3 here as the last statement of the main function. Now we are doing something important again in fun3. So here when we are calling to the fun3, we are going to the fun3, we can see that there is nothing left here to do in the main function. We are not using any variable after calling the fun3 function. So in this case, it's not legitimate to store anything for the main function, because after getting back from the fun3, we don't have anything left to do here in the main. Had we used any variable after calling fun3, that means something like this. Say I am writing a code to print, or I am doing something like this, say x0 equals to x0 plus 2. Then in that case, operating system would require to store the value of x, the array, into the stack. Then it would require to jump to the fun3. But since we are not having this statement anymore after calling of the fun3, when the fun3 completes, there is nothing left here in main. So it's not required to store the information of main anymore in this case. So in such cases, when the function call is the last statement and we don't have anything left in the caller function, then the compiler may skip the push operation into the stack and the operating system may not execute the stack operation at all. So it depends upon the compiler. Some compilers, if the compiler is clever one, all the modern compilers are so actually. So it skips the push operation into the stack in such cases when the function call is the very much last statement and there is nothing left after the function call in the caller function. So this is what happens during the function call in the memory. So we need to understand this in order to understand the recursion activity. So there it will be helpful. So thank you very much. Hope that you have enjoyed this.